Hello there, and welcome to the Sleepy Science Channel. I'm so grateful you found your way here tonight. Maybe the sound of waves has always called to you, or perhaps you're someone who finds peace in thinking about the vastness of water while drifting off to sleep. Either way, you're exactly where you need to be. Tonight's journey takes us beneath the surface, into the depths, across the currents, and through time itself as we explore the sea. The great blue expanse that covers more than 70% of our planet's surface, yet remains more mysterious than the surface of the moon. We'll discover how this immense body of water came to be, witness the strange and luminous creatures that inhabit its darkest depths, follow currents that circle the globe like a planetary heartbeat, and understand how every breath you take is connected to the ocean's ancient rhythms. Some of what you hear tonight might surprise you, some might comfort you, and hopefully all of it will carry you gently towards sleep while expanding your sense of wonder about the watery world that makes life on Earth possible. Before we begin our descent into the blue, if the calm explorations help you unwind at the end of your day, consider liking this video and subscribing to the channel. It helps others discover this peaceful corner of the internet, one sleepy explorer at a time. Now, let your breathing slow, your muscles relax, and your mind drift as we submerge ourselves into the story of the sea, the birth of the ocean. In the beginning, there was no ocean. Picture Earth as it existed 4.5 billion years ago, a molten ball of rock spinning through the darkness of space, its surface a churning sea of liquid stone, bombarded constantly by asteroids and comets, heated to temperatures where no liquid water could possibly exist. The young planet was a hostile place, utterly unrecognizable compared to the blue marble we know today. Yet, somewhere within that hellish landscape, the seeds of the ocean were already present, waiting for conditions to change. The water that would eventually fill Earth's ocean basins arrived through two primary mechanisms. The first and most widely accepted theory involves a process called outgassing. As Earth formed through the collision and accumulation of rocky material, water molecules became trapped within the minerals and rocks that made up the planet's interior. During a period of intense volcanic activity that followed Earth's initial formation, these water molecules, along with carbon dioxide, nitrogen, and other gases, were released from the planet's interior and shot into the atmosphere as water vapor. Imagine volcanoes more violent and numerous than anything seen in recorded human history, erupting continuously across the surface of the young Earth. With each eruption, they expelled not just lava and ash, but enormous quantities of water vapor and other gases. This wasn't the gentle steaming of modern hot springs, but rather a planetary-scale release of the components that would become our atmosphere and oceans. The water existed there all along, locked within the rocky material that coalesced to form our world. And now it was being liberated through the intense heat and pressure of volcanic outgassing. But the atmosphere at this time was far too hot for water to exist as a liquid. Temperatures exceeded 212 degrees Fahrenheit, the boiling point of water, so the expelled water vapor remained gaseous, accumulating in thick, dense clouds that wrapped the planet in a permanent shroud. Earth was wrapped in an atmosphere of steam, creating a greenhouse effect that kept surface temperatures scorching. This state persisted for perhaps hundreds of millions of years, a waiting period while the planet slowly, gradually cooled. The cooling happened for several reasons. The frequency of asteroid impacts decreased as the solar system matured, and most of the debris from its formation had either been swept up by planets or flung into distant orbits. Without the constant bombardment heating the surface, and as radioactive decay in Earth's interior began to slow, the planet's surface temperature began a long, gradual decline. The thick atmosphere of water vapor still trapped heat, but eventually a threshold was crossed. When Earth's surface temperature finally dropped below the boiling point of water, something extraordinary happened. The water vapor in the atmosphere began to condense. It started to rain. And it rained. And it rained. For centuries, possibly millennia, water fell from the sky in torrents that would dwarf any storm in modern times. The first permanent accumulations of liquid water appeared on Earth's surface approximately 3.8 to 4.4 billion years ago. Evidence for these ancient oceans comes from an unlikely source: tiny mineral grains called zircons found in Western Australia. These zircons, dated to about 4.4 billion years ago, have a chemical signature that indicates they formed in a cool, wet environment. They are fragments of a world that had already cooled enough for liquid water to exist, preserved through billions of years of geological tumult. The rainwater collected in the low-lying basins of Earth's surface, the depressions created by tectonic activity, and the random topography of the young crust. These basins filled slowly, drop by drop, storm by storm, until they overflowed and merged with neighboring basins. Water sought the lowest points, pulled by gravity into ever larger accumulations. Over geological timescales that are difficult for human minds to grasp, these separate bodies of water connected, expanded, and ultimately formed a single interconnected ocean that may have covered the entire planet. According to recent scientific studies, an ancient ocean likely covered the entire Earth about 150 million years after the planet's formation, roughly 4.4 billion years ago. This primordial ocean was vastly different from today's seas. There were no continents as we know them, perhaps only scattered volcanic islands rising from the water. The atmosphere contained no oxygen. The sky would have appeared a different color, perhaps orange or pink from the methane and carbon dioxide that dominated the air. But there's another chapter to the story of how water arrived on Earth. Some water may have been delivered from space itself. Comets, those icy wanderers from the outer solar system, bombarded the early Earth along with asteroids. Each impact brought not just destruction, but also a cargo of frozen water. Recent research examining the ratio of different hydrogen isotopes in Earth's water suggests that carbonaceous asteroids, ancient rocky bodies from the early solar system, may have been the primary delivery vehicle for a significant portion of Earth's water. The debate continues among scientists about the relative contributions of outgassing versus extraterrestrial delivery. But the consensus is emerging that both processes played a role. Perhaps 3/4 of Earth's water came from within, released through volcanic outgassing, while the remaining quarter arrived on the backs of comets and water-rich asteroids. Together, these sources created the ocean, the foundation for everything that would follow. The ocean didn't just form and remain static. As Earth's atmosphere continued to evolve, the chemistry of the ocean changed dramatically. By about 2 billion years ago, the ocean had achieved its modern chemical characteristics and sedimentation patterns. The water interacted with rocks, dissolving minerals. Volcanic gases continued to be released at mid-ocean ridges, where new crust formed. Life emerged and began to reshape the chemistry of both the ocean and atmosphere. Photosynthetic organisms started producing oxygen as a waste product, slowly but fundamentally altering the composition of seawater. The ocean that exists today is not the same ocean that formed 4 billion years ago. It has been renewed, recycled, and transformed countless times through the hydrological cycle. Water evaporates from the ocean's surface at a rate of about 1,080 cubic kilometers per day, and the same volume returns through precipitation. Every water molecule in the ocean has passed through this cycle many times, has been vapor in clouds, has fallen as rain on ancient landscapes, has flowed through rivers, has been locked in glaciers, has resided in the tissues of living things, and has returned again and again to the sea. The ocean's formation was not a single event, but a process, a gradual accumulation and transformation that took hundreds of millions of years. It required the planet to cool, the atmosphere to evolve, and countless volcanic eruptions to release water from the Earth's interior. It required bombardment from space, delivering additional water and organic compounds. It required time, vast stretches of time that make human history seem like a fleeting moment. And yet, here we are, living on a world where water covers most of the surface, where the ocean moderates climate, generates weather, produces oxygen, and provides habitat for an astonishing diversity of life. The ocean that laps at beaches, that sailors navigate, that scientists explore, that children play in, began as water vapor in volcanic plumes and ice in ancient comets. It condensed from clouds and rained for millennia, filling basins that would become the Atlantic, Pacific, Indian, Southern, and Arctic oceans, though in truth, it's all one interconnected body of water, one global ocean with arbitrary boundaries drawn by humans. As you rest tonight, consider that the water in your body, the water you drank today, has passed through the ocean many times. The hydrogen and oxygen atoms that make up water are ancient, formed in the hearts of stars or in the first moments after the Big Bang. That water has been ice in comets, vapor in Earth's early atmosphere, drops in the primordial ocean, and now, temporarily, it's part of you, before returning once again to the grand cycle. You are made of the ocean, and the ocean is in you. The ocean's physical architecture. The ocean is not simply a vast bathtub of water resting in a static basin. Its floor is as dynamic and complex as any continental landscape, constantly being created, destroyed, and reshaped by forces operating deep within the Earth. Understanding the architecture of the ocean basin requires understanding plate tectonics, the grand theory that revolutionized geology and explained how continents drift, mountains rise, and oceans open and close over hundreds of millions of years. Earth is composed of 3 main layers. the iron-rich core at the center, the semi-plastic mantle surrounding the core, and the thin outer crust, the solid shell on which we live. The crust beneath the oceans is fundamentally different from continental crust. Oceanic crust consists primarily of basalt, a dark, dense volcanic rock, while continental crust is mostly granite, which is lighter both in color and density. This difference in density explains why oceans exist where they do. Oceanic crust, being denser, sits lower on the mantle than continental crust. Water naturally flows to the lowest elevations, so the ocean basins, underlain by dense basaltic crust, became the repositories for Earth's water. It's not that water is covering land. Rather, the ocean basins are depressions in Earth's surface created by the nature of the underlying rock. The most dramatic feature of the ocean floor is the mid-ocean ridge system, the largest geological structure on the planet. This underwater mountain range extends more than 65,000 kilometers around the globe, winding through all the ocean basins like the seam on a baseball. The mid-Atlantic ridge runs down the center of the Atlantic Ocean, following the curves of the opposing coastlines of South America and Africa, Europe, and North America. In the Pacific, it's called the East Pacific Rise. In the Indian Ocean, the ridge forms an inverted Y shape. These ridges are not simply mountains on the seafloor. They are the places where new ocean floor is being born. Deep beneath the ridges, hot mantle material rises toward the surface, driven by convection currents in Earth's interior. As this material rises and the pressure decreases, it begins to melt, forming magma. The magma intrudes into the crust and erupts along the ridge axis, creating new oceanic crust through volcanic activity. The process can be imagined like pulling apart a piece of Play-Doh. As you stretch it, a thin spot forms in the middle. At mid-ocean ridges, tectonic plates are moving apart, and as they separate, magma rises to fill the gap, cooling underwater to form new ocean floor. This new crust is added to the edges of the diverging plates, which are carried away from the ridge at rates of a few centimeters per year, about the speed at which fingernails grow. This means that the ocean floor near mid-ocean ridges is young, recently formed, while oceanic crust far from the ridges is older, having had time to spread away from where it was created. When scientists sampled the actual seafloor rock through deep-sea drilling, they discovered that the farther rocks are from the ridge crest, the older they become. No oceanic crust older than about 200 million years has been found, because old oceanic crust doesn't last forever. On the opposite side of ocean basins from mid-ocean ridges, at the edges near continents or island arcs, old oceanic crust meets its end. Here, the seafloor descends into deep trenches, the deepest features on Earth's surface. Trenches are especially common in the Pacific Ocean, forming a ring of fire of intense geological activity. The Mariana Trench in the western Pacific reaches depths of nearly 11 kilometers below sea level, deeper than Mount Everest is tall. At these trenches, as one tectonic plate slides beneath another in a process called subduction. The dense oceanic crust, as it moves away from mid-ocean ridges and ages, eventually encounters either lighter continental crust or younger oceanic crust. Being denser, It bends downward and descends back into the mantle, where it is heated, melts, and is recycled back into the Earth's interior. This subduction process triggers earthquakes as the plates grind past each other and generates volcanic activity, as the descending plate releases water and other volatiles that cause the overlying mantle to melt. The ocean floor between the ridges where it's created and the trenches where it's destroyed is not flat. It contains vast abyssal plains, relatively flat regions covered by thick sediments that have accumulated over millions of years, settling slowly from the water column above. These plains are interrupted by seamounts, underwater mountains that rise from the seafloor, many of them extinct volcanoes that formed over hot spots in the mantle. Some seamounts rise high enough to break the surface as islands, like Hawaii, but many more remain submerged, hidden peaks in the underwater landscape. The ocean can be divided into distinct depth zones, each with characteristic conditions and life forms. The shallowest zone, from the surface down to about 200 meters, is the epipelagic or sunlight zone. Here, sunlight penetrates strongly enough for photosynthesis to occur, making it the realm of phytoplankton, the microscopic plants that form the base of most marine food webs. This is also where most fishing occurs, and where most of the familiar marine life, from dolphins to tuna to jellyfish, spend their time. Below 200 meters, sunlight begins to fade, and we enter the mesopelagic or twilight zone, extending down to about 1,000 meters. Here, there's still some dim light during the day, but not enough for photosynthesis. Many animals in this zone migrate vertically, rising toward the surface at night to feed and descending to darker depths during the day to avoid predators. This is the realm where bioluminescence becomes common, where creatures generate their own light to navigate the dim waters. From 1,000 to 4,000 meters lies the bathypelagic or midnight zone, where no sunlight penetrates at all. The water here exists in perpetual darkness, illuminated only by the bioluminescent flashes of the creatures that inhabit it. Pressure increases dramatically with depth, reaching 100 times surface pressure at 1,000 meters and 400 times surface pressure at 4,000 meters. Temperatures hover just above freezing. Life here has adapted to extraordinary conditions, developing specialized proteins, unique metabolisms, and strange body forms. Below 4,000 meters is the abyssopelagic or abyssal zone, reaching down to about 6,000 meters. Here, on the abyssal plains that cover much of the deep ocean floor, sediments accumulate grain by grain, creating a soft substrate that preserves the trails of creatures that crawl across it. Life is sparse but persistent, feeding on the rain of organic matter that sinks from the surface, the so-called marine snow of dead plankton, fecal pellets, and other detritus. Finally, in the deepest ocean trenches, from 6,000 meters down to the maximum depth of about 11,000 meters, lies the hadopelagic or Hadal zone, named after Hades, the ancient Greek underworld. The pressure here exceeds 1,000 times surface pressure, yet even in these extreme depths, life exists. Snailfish have been filmed at nearly 8,200 meters depth. Amphipods scuttle across the sediments, and bacterial mats cover the seafloor, all adapted to conditions that would crush and kill most organisms in seconds. The ocean's architecture is thus a study in extremes. From the sun-drenched surface to the crushing depths of trenches, from volcanic birth at mid-ocean ridges to recycling destruction at subduction zones, from abyssal plains to towering seamounts, the ocean floor is a landscape as varied and dynamic as any on land. It is constantly being remade through plate tectonics, a process so slow that humans can't perceive it directly, but so powerful that it has shaped the entire planet. The ocean basins we see today didn't exist 200 million years ago, and won't exist 200 million years in the future. They are temporary features on a planet that recycles its surface continuously, opening and closing ocean basins in a cycle that has repeated many times throughout Earth's history. The chemistry of seawater. When you taste seawater, the dominant sensation is salt. But that simple word, salt, conceals a remarkable complexity. Seawater is not just water with sodium chloride dissolved in it. It's a complex solution containing dozens of different dissolved elements, compounds, and ions, all in specific proportions that have remained remarkably constant over hundreds of millions of years, despite the constant addition of new material from rivers, volcanic vents, and the atmosphere. The average salinity of seawater is about 35 parts per thousand, meaning that if you evaporated 1 kilogram of seawater, you'd be left with about 30 grams of dissolved salts and minerals. The vast majority of this is sodium chloride, the same chemical compound we use as table salt. But seawater also contains significant amounts of magnesium, sulfate, calcium, potassium, and many other elements in smaller quantities. Every element found in Earth's crust can be detected in seawater if you look carefully enough. How did the ocean become salty? Most of the salts and dissolved elements were likely released through volcanic outgassing, along with the water itself. The primordial ocean was probably salty from the beginning, though its exact composition may have differed from today. Over billions of years, weathering of rocks on land has added more dissolved material as rivers carry ions from the continents to the sea. What's remarkable is that despite this constant input, the ocean's salinity hasn't increased dramatically over geological time. Various chemical and biological processes remove dissolved substances from seawater at roughly the same rate they're added, maintaining a dynamic equilibrium. Calcium is removed to form shells and skeletons of marine organisms, which eventually settle to the seafloor and form limestone. Chloride can be removed when seawater evaporates in shallow basins, forming salt deposits. Other elements are removed through precipitation as minerals, incorporation into marine sediments, or reactions with volcanic rock at mid-ocean ridges. Temperature in the ocean varies dramatically with location and depth. Near the surface, especially in tropical regions, water temperatures can exceed 30 degrees Celsius. At the poles, surface water can be near or even below the freezing point of fresh water, about -2 degrees Celsius, remaining liquid because salt lowers the freezing point. But below the surface layer, which is warmed by sunlight and stirred by wind and waves, temperature drops rapidly. There's a zone between about 200 and 1,000 meters depth where temperature decreases rapidly with depth. This thermocline acts as a barrier to vertical mixing, separating the warm, well-mixed surface layer from the cold, dense, deep ocean. Below the thermocline, temperature decreases more slowly and eventually levels off at about 2 to 4 degrees Celsius in the deep ocean, regardless of latitude. The vast majority of ocean water, by volume, is this cold, dark, deep layer. The warm surface waters we experience at beaches represent only a thin skin on top of a much larger, cold reservoir. The distribution of temperature in the ocean drives circulation patterns through differences in density. Cold water is denser than warm water, and salty water is denser than fresh water. When surface water in the North Atlantic or around Antarctica cools and becomes very cold, it also becomes very dense and sinks, driving deep water formation. This cold, dense water then flows along the ocean bottom toward the equator, eventually rising back to the surface in a process that can take hundreds or thousands of years. We'll explore these circulation patterns more in the next section, but the chemistry of seawater, its temperature and salinity, are the driving forces. Another critical aspect of seawater chemistry is its pH, a measure of acidity or alkalinity. Prior to human industrial activity, the ocean's pH was about 8.2, making it slightly alkaline. The ocean acts as a massive buffer, absorbing carbon dioxide from the atmosphere and maintaining relatively stable pH despite large changes in atmospheric composition over geological time. When carbon dioxide dissolves in seawater, it reacts to form carbonic acid, which can then break down into bicarbonate and carbonate ions. This chemical system allows the ocean to absorb vast amounts of carbon dioxide, acting as a crucial regulator of Earth's climate. However, since the beginning of the Industrial Revolution, the ocean has absorbed about a third of the carbon dioxide released by human activities. This absorption is causing ocean acidification, a decrease in pH that has already lowered the ocean's average pH by about 0.1 units, representing a 30% increase in acidity. This might sound small, but pH is a logarithmic scale, and even small changes can have significant effects on marine life, especially organisms that build shells or skeletons from calcium carbonate, like corals, mollusks, and many plankton species. As the ocean becomes more acidic, it becomes more difficult for these organisms to build and maintain their calcium carbonate structures. Dissolved oxygen is another critical component of seawater chemistry. Oxygen enters the ocean at the surface through a change with the atmosphere and through photosynthesis by marine plants and phytoplankton. Surface waters are typically well oxygenated, but oxygen decreases with depth. In some regions, at intermediate depths, there are oxygen minimum zones where dissolved oxygen drops to very low levels. These zones occur where organic matter sinking from the surface is decomposed by bacteria, consuming oxygen faster than it can be replenished by circulation. The ocean also contains dissolved nutrients essential for life, including nitrogen, phosphorus, and iron. These nutrients are often the limiting factors for biological productivity. In surface waters, nutrients are consumed by phytoplankton and become incorporated into organic matter. When organisms die and sink, they carry these nutrients to the deep ocean. As a result, surface waters, especially in the tropics, are often nutrient poor. while deep waters are nutrient-rich. Upwelling, the process by which deep water rises to the surface, brings these nutrients back to the sunlit zone, creating areas of high productivity that support abundant marine life and important fisheries. Understanding the chemistry of seawater is essential for understanding how the ocean functions as an ecosystem, how it interacts with the atmosphere and climate, and how it responds to human impacts. The ocean is not just a body of water. It's a complex chemical system, finely tuned over billions of years of evolution, capable of buffering against change, but not infinitely resilient. The chemistry we observe today is the result of ongoing processes, a balance between inputs and outputs, between mixing and stratification, between life and geology, all operating simultaneously across the vast expanse of the global ocean. Currents, the ocean's circulatory system. The ocean is never still. Even when its surface appears calm, currents move ceaselessly beneath, driven by wind, differences in temperature and salinity, the rotation of the Earth, and the gravitational pull of the Moon and Sun. These currents form a global circulation system that transports heat, nutrients, and organisms around the planet, profoundly influencing climate, weather, and the distribution of marine life. Surface currents, occupying roughly the upper 400 meters of the ocean, are primarily driven by wind. The major wind belts of Earth, the trade winds in the tropics, the westerlies in mid-latitudes, and the polar easterlies near the poles, blow across the ocean surface, dragging water along and creating broad current patterns. But because Earth rotates, these currents don't flow in straight lines. They curve to the right in the northern hemisphere and to the left in the southern hemisphere, an effect called the Coriolis effect. This combination of wind-driven flow and Earth's rotation creates large circular current systems called gyres. There are 5 major ocean gyres: the North Atlantic Gyre, the South Atlantic Gyre, the North Pacific Gyre, the South Pacific Gyre, and the Indian Ocean Gyre. Each gyre circulates clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. The currents on the western sides of these gyres, like the Gulf Stream in the Atlantic, the Kuroshio Current in the Pacific, are particularly strong and narrow, transporting warm, tropical water toward higher latitudes at speeds that can exceed 2 meters per second. The Gulf Stream, perhaps the most studied ocean current, originates in the Gulf of Mexico, flows northward along the eastern coast of the United States, and then crosses the Atlantic toward Europe. It carries more than 30 times the flow of all the world's rivers combined. The warm water it transports releases heat to the atmosphere as it moves northward, moderating the climate of northwestern Europe. Without the Gulf Stream, countries like the United Kingdom and Norway would experience much colder winters, more similar to the climate of Labrador or Alaska at the same latitude. While surface currents are important for transporting heat and influencing regional climates, there's an even larger circulation system operating in the deep ocean. This deep circulation, called thermohaline circulation, or the global ocean conveyor belt, is driven not by wind, but by differences in temperature and salinity, which affect water density. The process begins in the North Atlantic and around Antarctica, where surface water becomes very cold and salty. In the North Atlantic, between Greenland and Scandinavia, surface water cooled by Arctic winds and made saltier by sea ice formation becomes so dense that it sinks to the ocean floor. This deep water, called North Atlantic deep water, then flows southward along the bottom of the Atlantic Ocean, crosses the equator, and eventually reaches the Southern Ocean around Antarctica. Here it meets another mass of cold, dense water formed around the Antarctic continent and flows eastward into the Indian and Pacific Oceans. The deep water gradually warms and rises back toward the surface through slow mixing and upwelling, particularly in the Pacific and Indian Oceans. Once at the surface, it begins to flow back toward the Atlantic, completing the circulation. This entire journey can take 1,000 years or more. A water molecule that sank in the North Atlantic might not return to the surface until it reaches the North Pacific a millennium later. This thermohaline circulation is crucial for Earth's climate because it redistributes heat around the planet. It also affects the distribution of nutrients and dissolved gases, including oxygen and carbon dioxide. Deep water formation brings oxygen-rich surface water to the deep ocean, while upwelling brings nutrient-rich deep water back to the surface where it can fuel biological productivity. Changes in this circulation, whether from natural variability or human-induced climate change, can have profound effects on global climate patterns. Tides represent another form of ocean motion, though one driven not by wind or density differences, but by gravitational forces. The moon's gravity pulls on Earth's water, creating a bulge on the side of Earth facing the moon. Interestingly, there's also a bulge on the opposite side of Earth, created not by the moon pulling harder there, but by inertial effects as Earth and Moon orbit their common center of mass. As Earth rotates beneath these two bulges, any given location on the coast experiences 2 high tides and 2 low tides each day, separated by about 6 hours. The Sun also exerts gravitational pull on Earth's water, though its effect is smaller than the Moon's because it's much farther away. When the Sun and Moon align during new and full moons, their gravitational pulls combine to create larger than normal tides called spring tides. When the Sun and Moon are at right angles to each other during the first and last quarter moons, their pulls partially cancel out, creating smaller neap tides. Tides do more than raise and lower sea level at the coast. They create strong tidal currents as water flows in and out of bays, estuaries, and channels. In some locations, these currents can exceed several meters per second, strong enough to create standing waves and powerful whirlpools. Tides also drive mixing between coastal and offshore waters, bringing nutrients from rivers and the seafloor into the open ocean and affecting the distribution of marine organisms. On smaller scales, the ocean contains countless eddies, swirling masses of water that break off from major currents and drift across the ocean basins. Some eddies rotate clockwise, others counterclockwise. Some contain warm water trapped from tropical regions and transported into cooler waters. Others contain cold water trapped from polar regions. These eddies can persist for months or years, slowly dissipating as they mix with surrounding water. They transport heat, salt, nutrients, and organisms, creating patches of different conditions within the otherwise relatively uniform open ocean. The ocean's circulation system is thus extraordinarily complex, operating at scales from millimeters to the entire planet, from seconds to millennia. Wind-driven surface currents, density-driven deep circulation, tides, eddies, and countless other processes all contribute to the constant motion of the sea. This motion is not random chaos, but follows patterns determined by the forces acting on the ocean. The sun's heat, the moon's gravity, Earth's rotation, the shape of ocean basins, and the eternal drive toward equilibrium that moves heat from warm regions to cold, mixes water of different densities, and maintains the dynamic, steady state that characterizes the ocean system. Understanding ocean currents is essential for navigation, for predicting weather and climate, for managing fisheries, for tracking pollution, and for countless other human activities. But beyond its practical importance, the ocean's circulation represents one of nature's grand phenomena, a planetary scale system that has operated for billions of years, transporting water, heat, and life around the globe in an endless, flowing dance. Life in the sunlit waters. When we think of life in the ocean, we often picture large, charismatic animals, dolphins leaping through waves, sea turtles gliding through coral gardens, whales breaching at the surface. But the most important organisms in the ocean are microscopic, invisible to the naked eye, yet more numerous than stars in the galaxy. These are the phytoplankton, single-celled organisms that drift in the sunlit surface waters, capturing solar energy through photosynthesis and forming the foundation of almost all ocean food webs. Phytoplankton, primarily single-celled algae and cyanobacteria, are found wherever there's light and nutrients in the ocean. Their ancestors emerged at least 2.3 billion years ago, and they literally changed the world. Cyanobacteria were likely the first organisms capable of oxygenic photosynthesis, converting sunlight into energy while releasing oxygen as a waste product. Over hundreds of millions of years, these tiny organisms produced enough oxygen to fundamentally alter Earth's atmosphere, creating the oxygen-rich air we breathe today. Modern phytoplankton continue this vital work. Through photosynthesis, they produce roughly half of the oxygen in Earth's atmosphere, making every other breath you take a gift from these microscopic ocean dwellers. They also form the base of marine food webs. Zooplankton, tiny animals and larvae, graze on phytoplankton. Small fish eat zooplankton. Larger fish eat small fish. And so the energy captured by phytoplankton flows upward through the food web, ultimately supporting everything from sardines to sharks, from anchovies to whales. The abundance of phytoplankton varies dramatically across the ocean. In tropical regions, strong stratification keeps nutrient-rich deep water separated from the sunlit surface, limiting productivity despite abundant light. These are the ocean's deserts, beautiful and blue, but relatively empty of life. In polar regions, and in areas where deep water upwells to the surface, nutrients are abundant. Here, when light conditions permit, phytoplankton bloom in enormous numbers, turning the water green or brown and supporting rich ecosystems. The most diverse and productive ecosystems in the ocean are found in relatively shallow coastal areas and on coral reefs. Coral reefs, often called the rainforests of the sea, occupy less than 1% of the ocean floor but support approximately a quarter of all marine species. Reefs are built by tiny animals called coral polyps, which secrete calcium carbonate skeletons and live in symbiosis with photosynthetic algae called zooxanthellae. The algae live within the coral's tissues, capturing sunlight and producing sugars that feed the coral, while the coral provides the algae with shelter and nutrients. This partnership allows corals to thrive in nutrient-poor tropical waters, building massive limestone structures that provide habitat for countless other species. Reef fish display every color imaginable, from brilliant yellows and blues to stark blacks and whites, often with patterns that help them blend into the complex reef background or warn predators of their toxicity. Sea turtles graze on sea grasses and algae or hunt for jellyfish and sponges. Octopuses hide in crevices, changing color to match their surroundings. Sharks patrol the reef edges, maintaining population balance among prey species. But coral reefs face severe threats. Rising ocean temperatures cause coral bleaching, a stress response where corals expel their symbiotic algae, losing their color and their primary food source. If stress continues, corals can die. Ocean acidification makes it harder for corals to build their skeletons. Pollution, overfishing, and physical damage from anchors and careless divers all take their toll. Many reefs that were vibrant ecosystems just decades ago are now degraded, reduced to algae-covered rubble with few living corals remaining. Coastal zones, where ocean meets land, support dense concentrations of life adapted to conditions that change with the tides. In the intertidal zone, the area between high and low tide marks, organisms must tolerate both immersion in seawater and exposure to air. Barnacles cement themselves to rocks, closing their shells tightly when exposed, and opening to filter feed when submerged. Sea anemones retract their tentacles and wait patiently for the tide to return. Crabs scuttle sideways across the beach, seeking prey or hiding from predators. Tide pools, pockets of water left behind when the tide recedes, become temporary aquaria containing fish, urchins, starfish, and myriad invertebrates, all adapted to survive in a small, isolated habitat until the next high tide reconnects them with the ocean. Kelp forests, found in cool, nutrient-rich waters along many temperate coasts, create underwater forests as complex as any terrestrial woodland. Giant kelp, a type of brown algae, can grow more than half a meter per day, reaching lengths exceeding 30 meters. The kelp forms a canopy at the surface where blades spread out to capture maximum sunlight, while holdfasts anchor the algae to rocks below. Within this forest structure, sea otters wrap themselves in kelp fronds while resting at the surface. Sea urchins graze on kelp, sometimes overgrazing and creating barren areas where kelp can no longer grow. Fish find shelter among the swaying fronds. Harbor seals hunt for prey among the kelp. The entire ecosystem depends on the kelp's productivity and structure. Marine mammals, though they descended from terrestrial ancestors, are now fully adapted to ocean life. Whales, the largest animals ever to exist on Earth, range from the massive blue whale, which can exceed 30 meters in length and 150 tons in mass, to smaller species like the narwhal and beluga. Whales are divided into two groups: baleen whales, which filter small prey from the water using comb-like baleen plates, and toothed whales, which actively hunt fish, squid, and sometimes other marine mammals. Dolphins and porpoises, members of the toothed whale group, are highly intelligent, social animals that navigate and hunt using echolocation, emitting clicks and listening for echoes to build a sonic picture of their surroundings. Seals, sea lions, and walruses form another group of marine mammals that return to land to breed but spend most of their time in the water hunting fish and invertebrates. Unlike whales, which cannot return to land at all, these pinnipeds retain functional hind limbs, though these are modified into flippers more suited for swimming than walking. Sea otters, smallest of the marine mammals, rarely come ashore, spending their entire lives in coastal kelp forests, where they float on their backs while eating or sleeping, often wrapping themselves in kelp to avoid drifting away. Sharks, some of the ocean's most successful predators, have existed for more than 400 million years, predating the dinosaurs. They range from the massive whale shark, largest fish in the ocean, which filter feeds on plankton, to the great white shark, apex predator of temperate coasts, to strange deep-sea species that will be discussed in the next section. Most sharks have acute senses, including the ability to detect electrical fields produced by the muscles of prey animals, allowing them to hunt even in murky water or darkness. Despite their fearsome reputation, sharks are far more threatened by humans than we are by them. Overfishing has decimated many shark populations, with some species declining by more than 90%. The sunlit surface ocean, despite its familiarity and accessibility, remains full of mysteries. New species are discovered regularly. Migration patterns of marine animals continue to surprise researchers. The complex interactions among species, the ways populations respond to environmental changes, the impacts of human activities on marine ecosystems, all remain active areas of research. But one thing is clear: the sunlit zone of the ocean is teeming with life, from microscopic phytoplankton to the largest animals on Earth, all interconnected in complex food webs, all adapted to the opportunities and challenges of life in the sea, the Twilight Zone and beyond. Below the bright, familiar waters of the sunlit zone lies a realm of perpetual twilight, then complete darkness. Here, in the mesopelagic zone from 200 to 1,000 meters depth, light fades to almost nothing, but it doesn't disappear entirely. During the day, dim blue light filters down from above, barely enough to see by, but enough that predators can still hunt by sight and prey must hide or camouflage themselves. At night, even this faint glow vanishes, and the ocean enters a darkness deeper than any moonless night on land. It is in this dim realm, and in the darker depths below, that one of nature's most extraordinary phenomena becomes commonplace: bioluminescence. Studies have shown that 76% of marine organisms observed in deep waters have the capability to produce their own light, making bioluminescence not an exotic rarity, but a fundamental characteristic of life in the deep ocean. Bioluminescence is the production of light through a chemical reaction within an organism's body. At its heart is the interaction between a light-emitting molecule called luciferin and an enzyme called luciferase. When luciferin combines with oxygen in the presence of luciferase, it undergoes oxidation, releasing energy in the form of light. This reaction is remarkably efficient, converting nearly all the energy into light rather than heat, making it a cold light that doesn't warm the animal producing it. Why would deep-sea creatures evolve to produce light? The answers are as varied as the animals themselves. Some use bioluminescence as a lure, attracting prey within striking distance. Others use it as a searchlight to find prey in the darkness. Still others use it for camouflage, creating a counter-illumination effect that hides their silhouette from predators looking up from below. Many use species-specific patterns of light as signals to identify potential mates in the vast, dark expanse where finding another member of your own species is a significant challenge. The evolution of bioluminescence represents a remarkable example of convergent evolution. Scientists estimate that bioluminescence has evolved independently at least 40 separate times in marine organisms, driven by the unique challenges of life in the dark ocean. It first appeared in single-celled organisms billions of years ago, and has since been adopted and modified by bacteria, algae, jellyfish, worms, crustaceans, squid, and fish, each developing their own variations on the theme. Most bioluminescent organisms produce blue-green light because these shorter wavelengths travel farther through seawater than longer wavelengths like red. This makes blue-green light the most efficient color for communication and other light-based functions in the ocean. Interestingly, many deep-sea creatures are colored red because red light doesn't penetrate to their depths, making them appear black and effectively invisible in their environment. Perhaps the most famous bioluminescent predator is the deep-sea anglerfish. Female anglerfish have a fishing rod-like structure extending from the top of their heads, with a glowing lure, called an esca, at its tip. This lure contains symbiotic bioluminescent bacteria that produce light, attracting curious prey close enough for the anglerfish to strike with its large mouth and razor-sharp teeth. The anglerfish doesn't produce the light itself, but maintains colonies of bacteria in a specialized organ, providing them with nutrients and receiving light in return. Other creatures use bioluminescence defensively. The vampire squid, a small, gelatinous creature despite its fearsome name, ejects a sticky, bioluminescent mucus when threatened. This glowing cloud can startle and confuse predators, giving the squid time to escape into the darkness. Some jellyfish create spectacular light shows when disturbed, flashing brilliant patterns that may serve to startle predators or attract larger predators that might eat whatever is attacking the jellyfish. For many species, bioluminescence serves a critical role in reproduction. In the vast darkness, finding a mate is challenging, and species-specific light patterns act like advertisements, allowing individuals to identify potential partners of their own species. Lanternfishes, one of the most diverse families of deep-sea fishes with more than 2,000 species, have complex patterns of photophores, light-producing organs arranged uniquely in each species, allowing for precise species recognition even in complete darkness. The twilight zone and deeper waters are not just about light, they're about surviving extreme conditions. Pressure increases by approximately 1 atmosphere, about 14.7 pounds per square inch, for every 10 meters of depth. At 1,000 meters, pressure is 100 times greater than at the surface. At 4,000 meters, it's 400 times greater. This pressure would instantly crush most terrestrial organisms, collapsing airspaces and breaking down cellular structures. Deep-sea creatures have evolved remarkable adaptations to survive these pressures. Many have soft, gelatinous bodies with few or no gas-filled spaces. Their cells contain special proteins and other molecules that remain stable under high pressure. Some deep-sea fish have a watery, almost jelly-like flesh that seems hardly substantial enough to be called muscle. But this structure is precisely what allows them to function in their high-pressure environment. Food is scarce in the deep ocean. There are no plants because there's no light for photosynthesis. Most nutrition comes from above, as dead organisms and fecal pellets sink slowly through the water column, a rain of organic matter called marine snow. Deep-sea creatures are often remarkably efficient at capturing and utilizing whatever food they can find. Many have expandable stomachs that allow them to swallow prey larger than themselves, a crucial adaptation when meals are rare and unpredictable. Some deep-sea fish have evolved enormous jaws and teeth out of proportion to their small bodies. The black swallower can swallow prey more than twice its own length, its stomach stretching to accommodate the meal. The viperfish has teeth so long that it cannot fully close its mouth. But these fearsome fangs effectively impale prey. Many deep-sea predators have large eyes adapted to gather every available photon of light, whether from bioluminescence or the faint downwelling light in the twilight zone. Other species have taken the opposite approach, losing their eyes entirely. In the deepest parts of the ocean, where no light penetrates, eyes serve no purpose and may actually be a liability, requiring energy to maintain and potentially providing an entry point for parasites. These eyeless species rely instead on other senses: sensitive lateral lines that detect vibrations, chemoreceptors that taste the water for signs of prey, and other adaptations we're only beginning to understand. Some creatures have evolved remarkable transparency. The glass squid, for example, is almost entirely see-through, rendering it nearly invisible in the water column, even when illuminated by bioluminescence. Only its eyes remain visible, appearing as small, dark spots that might be mistaken for seeds or tiny particles. This transparency serves as effective camouflage in an environment where hiding from predators is essential for survival. The diversity of life in the twilight zone and deeper waters continues to astound researchers. Every deep-sea expedition discovers new species, and many areas of the deep ocean have never been explored. We know more about the surface of Mars than we do about most of the deep ocean. The creatures that inhabit these depths have evolved in isolation for millions of years, developing body forms, behaviors, and biochemistry that seem alien compared to life in shallow waters. Yet, despite their strangeness, these deep-sea organisms are part of the same evolutionary tree as surface dwellers. They face the same fundamental challenges: finding food, avoiding predators, reproducing, surviving in their environment. They've simply found different solutions shaped by the unique conditions of life in the dark, cold, high-pressure depths. And many of these solutions involve bioluminescence, that cold light that turns the deep ocean into a constellation of living stars, a hidden universe of glowing creatures that most humans will never see, carrying on their quiet lives in the largest habitat on Earth. The deep ocean floor. The deepest parts of the ocean have been explored less thoroughly than the surface of the moon. Fewer than 20 people have descended to the deepest spot in the ocean, the Challenger Deep in the Mariana Trench, compared to the 12 who have walked on the lunar surface. Yet these depths, and the slightly shallower but still extreme environments of the abyssal plains and other deep-sea floors, harbor ecosystems that challenge our understanding of life's requirements and expand our sense of where and how organisms can survive. For decades, scientists assumed that the deep ocean floor was a barren desert, devoid of life except for a few scavenging organisms. The depths were cold, dark, under crushing pressure, and seemingly empty of the nutrients needed to support complex ecosystems. But in 1991, during an expedition to the Galapagos Rift, using the submersible Alvin, researchers made a discovery that revolutionized our understanding of deep-sea ecosystems: hydrothermal vents. These vents occur at mid-ocean ridges where tectonic plates spread apart and magma rises near the seafloor. Cold seawater seeps down through cracks in the volcanic rock, is heated by the magma to temperatures exceeding 400 degrees Celsius, dissolves minerals from the rock, and then shoots back out through chimney-like structures. The emerging water is loaded with dissolved chemicals including hydrogen sulfide, which is poisonous to most life forms but essential for the bacteria that form the foundation of hydrothermal vent ecosystems. These bacteria perform chemosynthesis, using the chemical energy in hydrogen sulfide and other compounds to build organic molecules, much as plants use light energy for photosynthesis. The bacteria form mats on surfaces near vents and also live symbiotically inside the tissues of larger organisms. Giant tube worms, taller than a human, have no digestive system. They rely entirely on symbiotic bacteria that live in specialized organs within their bodies, converting hydrogen sulfide into nutrients that feed the worm. The ecosystem around hydrothermal vents is astonishing. In addition to tube worms, there are clams the size of dinner plates, white crabs that swarm over surfaces, shrimp with no eyes but with light-detecting organs on their backs, possibly used to sense the faint glow of heated vent water. These ecosystems are oases in the deep sea, supporting abundant life, not through sunlight and photosynthesis, but through geothermal energy and chemosynthesis. They represent a fundamentally different way of powering an ecosystem, one that could potentially exist on other worlds where liquid waters and geothermal energy occur, even in the absence of sunlight. Beyond hydrothermal vents, the abyssal plains that cover much of the deep ocean floor support sparser but still remarkable life. The sediments here are soft and fine, composed of microscopic shells of planktonic organisms that have sunk from the surface over millions of years, along with dust blown from continents and volcanic ash from submarine eruptions. The accumulation rate is slow, perhaps a few centimeters per 1,000 years, but over geological time, these sediments can be hundreds of meters thick. Life on the abyssal plains includes a variety of specialized organisms. Sea cucumbers, relatives of starfish and sea urchins, crawl slowly across the sediment surface, ingesting mud and extracting whatever organic matter it contains. Some look like plump sausages, others like translucent ghosts, and still others have bizarre appendages that they use to sweep the water for food. Brittle stars, with 5 long, flexible arms, filter feed on particles suspended in the water or use their arms to crawl across the bottom. Various fish adapted to the abyss include rat tails, with large heads tapering to thin, rat-like tails, and the aptly named blobfish, whose gelatinous, loose flesh allows it to withstand extreme pressure without expending energy. Amphipods, shrimp-like crustaceans, are abundant scavengers. Some species grow to enormous sizes compared to their shallow water relatives, reaching more than 30 centimeters in length. When food falls to the seafloor, such as a dead whale or fish, these amphipods can swarm by the thousands, stripping flesh from bones in a matter of days. The deep ocean trenches, the deepest features on Earth, reach depths exceeding 10,000 meters. Here, at the very bottom of the Hadal zone, pressure exceeds 1,000 atmospheres, more than 8 tons per square inch. Temperatures hover near freezing. Yet even here, life exists. Snailfish have been filmed at depths greater than 8,000 meters, holding the record for deepest fish ever observed. These animals have translucent, gelatinous bodies, small eyes, and strange, almost tadpole-like appearances. They survive by eating amphipods and other small invertebrates that scuttle across the trench floor. The sediments in trenches are often different from those on abyssal plains because trenches occur where tectonic plates converge. Sediments can include material scraped from the subducting plate, creating a complex geology. Organic matter may accumulate in trenches because the steep walls funnel sediment to the bottom. This concentration of nutrition supports the communities of scavengers and detritivores that inhabit these extreme depths. One of the most fascinating discoveries about deep-sea sediments is the presence of xenophyophores, giant single-celled organisms that can reach 10 centimeters or more in diameter. These bizarre creatures are among the largest single-celled organisms known, though they achieve this size by remaining mostly hollow, with their cytoplasm spread in a thin layer. They feed on bacteria and other microorganisms in the sediment, playing an important but still poorly understood role in deep-sea nutrient cycling. Bacterial life is abundant in deep-sea sediments, existing meters below the seafloor and surviving on minimal energy from chemical reactions. Some of these bacteria metabolize extremely slowly, dividing perhaps once per century or even less frequently. They represent a form of life at its minimum, barely active but persistent, surviving in conditions of near total energy deprivation. Studies of these deep biosphere microbes are expanding our understanding of life's lower limits and informing the search for life on other planets or moons where conditions might be similarly extreme. The deep ocean floor is not a single uniform environment, but a mosaic of habitats. each with its own conditions and communities. From the energetic chaos of hydrothermal vents to the quiet monotony of abyssal plains, from the crushing depths of trenches to the peculiar ecosystems of cold seeps, where methane and other hydrocarbons seep from the seafloor. The deep ocean is far more diverse and alive than early scientists imagined. Every expedition that descends into these depths returns with new species, new observations, and new questions about how life adapts, survives, and thrives in the Earth's most extreme marine environments. The ocean's role in climate. The ocean is not a passive component of Earth's climate system. It is an active, dynamic player that profoundly influences temperature, precipitation, and weather patterns around the globe. Understanding climate requires understanding the ocean's role in storing and transporting heat, absorbing and releasing gases, and interacting with the atmosphere in complex feedback loops that operate over time scales from days to millennia. Water has an enormous capacity to store heat compared to land or air. The ocean acts as a massive heat reservoir, absorbing solar energy at the surface, particularly in tropical regions, and storing that heat in its vast volume. As warm water moves from the tropics toward the poles through ocean currents, it releases this heat to the atmosphere, moderating temperatures and influencing weather. This heat transport is why Western Europe enjoys a much milder climate than Eastern Canada at the same latitude. The Gulf Stream and North Atlantic Drift carry warm water northward, releasing heat that keeps European winters surprisingly temperate. The ocean's role in the carbon cycle is equally important. Currently, the ocean absorbs about 1/3 of the carbon dioxide released by human activities, removing this greenhouse gas from the atmosphere and temporarily storing it in solution. This absorption occurs through both physical and biological processes. At the surface, carbon dioxide dissolves directly into seawater. The amount that dissolves depends on temperature, with cold water able to hold more dissolved gas than warm water. As surface water cools at high latitudes and sinks, it carries dissolved carbon dioxide into the deep ocean, where it can remain sequestered for hundreds or thousands of years until that water eventually returns to the surface. Photosynthetic organisms in the ocean also play a crucial role in the carbon cycle. Phytoplankton take up carbon dioxide, convert it into organic compounds, and incorporate it into their bodies. When these organisms die and sink, they carry carbon to the deep ocean. Some of this carbon is consumed by organisms in the water column or on the seafloor and released back as carbon dioxide. But some reaches the sediments and is buried, effectively removing it from the active carbon cycle for millions of years. This biological pump has been operating throughout Earth's history, and the limestone rocks and oil deposits around the world are testament to the enormous amounts of carbon that the ocean has captured and stored over geological time. However, the ocean's ability to absorb carbon dioxide is not unlimited. As mentioned earlier, absorption causes ocean acidification, changing the chemistry of seawater with potentially severe consequences for marine life. Additionally, as the ocean warms, its capacity to dissolve gases decreases. A warmer ocean will absorb less carbon dioxide from the atmosphere, potentially creating a positive feedback loop where warming reduces absorption, leaving more carbon dioxide in the atmosphere, causing more warming. The ocean also influences climate through its effect on precipitation patterns. Water evaporated from the ocean's surface forms clouds and eventually falls as rain or snow. The amount of evaporation depends on ocean surface temperature, with warm waters evaporating more readily than cold. This is why the tropics, with warm ocean waters, tend to be wet, while regions with cold surface waters often have dry climates. Changes in ocean circulation patterns or temperatures can thus cause shifts in where rain falls, potentially leading to droughts in some areas and floods in others. El Niño and La Niña are prime examples of how ocean-atmosphere interactions affect climate. These are opposite phases of a natural cycle in the tropical Pacific Ocean, where sea surface temperatures alternate between warmer than normal and cooler than normal every few years. During El Niño, warm water accumulates in the eastern Pacific, suppressing the upwelling of cold, nutrient-rich water along the South American coast. This changes atmospheric circulation patterns, affecting weather around the globe. North America may experience wetter winters, while Southeast Asia and Australia experience drought. La Niña, the opposite phase, brings cooler surface temperatures to the eastern Pacific and its own set of global climate effects. These are not isolated events, but part of the ongoing, complex interaction between ocean and atmosphere. Heat and moisture from the ocean fuel tropical cyclones, the hurricanes and typhoons that can cause devastating damage to coastal areas. The ocean's currents redistribute heat, preventing the tropics from becoming unbearably hot and the poles from becoming even colder than they are. The ocean's thermal inertia, its resistance to rapid temperature change, smooths out seasonal variations and moderates climate extremes. Climate change is altering the ocean in numerous ways. Ocean temperatures are rising as the ocean absorbs more than 90% of the excess heat trapped by increased greenhouse gases. This warming causes the ocean to expand, contributing to sea level rise. Combined with water added from melting glaciers and ice sheets, sea level has risen about 20 centimeters since the beginning of the 20th century and is accelerating. Rising seas threaten coastal communities, infrastructure, and ecosystems. Changes in ocean circulation patterns are also occurring. Melting ice in the Arctic and Greenland is adding fresh water to the North Atlantic, potentially slowing the formation of deep water and weakening the thermohaline circulation. If this circulation were to significantly slow or stop, it could have dramatic effects on regional and global climate, potentially cooling northwestern Europe and disrupting precipitation patterns worldwide. The ocean is also experiencing deoxygenation, a decrease in dissolved oxygen caused by warming and nutrient pollution. Warmer water holds less oxygen, and increased stratification reduces mixing between surface and deep waters, limiting oxygen supply to the deep ocean. Nutrient pollution from agriculture and sewage causes algal blooms that consume oxygen when they die and decompose, creating dead zones where most marine life cannot survive. Understanding the ocean's role in climate is essential for predicting future climate change and its impacts. Climate models must accurately represent ocean processes to make reliable projections. Monitoring ocean temperature, salinity, circulation, and chemistry provides crucial data for detecting climate change and its effects. The ocean and atmosphere are intimately coupled, two parts of a single, integrated Earth system, and changes in one inevitably affect the other. As humans continue to alter atmospheric composition and thus climate, the ocean responds, absorbing heat and carbon dioxide, changing its chemistry and circulation, and ultimately affecting the climate system it helped to stabilize for millions of years. Human connections and impacts. Humans have been connected to the ocean since our earliest days as a species. Coastal areas provided abundant food, facilitated travel and trade, and shaped the development of civilizations. Ancient peoples developed sophisticated knowledge of tides, currents, and marine life. Polynesians navigated vast stretches of the Pacific using only observations of stars, waves, and wildlife, discovering and settling islands separated by thousands of kilometers of open ocean. The Phoenicians established trade networks throughout the Mediterranean. Vikings crossed the Atlantic to reach North America centuries before Columbus. Ocean exploration has a long and rich history, but for most of human history, knowledge of the ocean was limited to its surface and shallow coastal waters. The development of diving equipment, beginning with simple diving bells and progressing to modern scuba gear and submersibles, has allowed humans to directly observe and study underwater environments. The invention of sonar, which uses sound waves to map the seafloor, revealed the ocean's topography for the first time. Satellites can now measure sea surface temperature, detect ocean currents, and monitor changes in sea level from space. Despite these advances, much of the ocean remains unexplored. More than 80% of the ocean has never been mapped in detail. Most deep-sea environments have never been visited by humans or robots. New species are discovered regularly, and entire ecosystems remain unknown. The ocean is Earth's last great frontier, a realm of mystery and discovery that continues to surprise and challenge us. Humans have long extracted resources from the ocean. Fishing has been a crucial food source for coastal populations throughout history, and modern industrial fishing fleets can harvest enormous quantities of fish. Unfortunately, this has led to overfishing, with many populations depleted to a fraction of their historical abundance. Large predatory fish like tuna, swordfish, and sharks have declined by more than 90% in many regions. Some fisheries have collapsed entirely, unable to recover even after decades of reduced fishing pressure. The problem extends beyond direct fishing pressure. Modern fishing methods, including bottom trawling, which drags heavy nets across the seafloor, destroy habitat and catch enormous amounts of unintended species called bycatch. Bottom trawling can devastate deep-sea ecosystems that took thousands of years to develop, turning complex gardens of bioluminescent corals and diverse life into rubble in a single pass. Longline fishing, which uses lines with thousands of baited hooks stretching for many kilometers, catches seabirds, sea turtles, and marine mammals along with target species. Sustainable fishing practices exist and can allow fish populations to recover while still providing food and livelihoods. These include catch limits based on scientific assessments of population health, restrictions on gear types that cause excessive bycatch or habitat damage, and the establishment of marine protected areas where fishing is prohibited. allowing ecosystems to function without human extraction. Some fisheries are well managed and sustainable, but many are not, and global fish consumption continues to increase as human population grows. Pollution affects the ocean in numerous ways. Nutrient pollution from agricultural runoff and sewage causes harmful algal blooms and creates dead zones depleted of oxygen. Chemical pollutants, including pesticides, industrial chemicals, and pharmaceuticals, accumulate in marine food webs, sometimes reaching toxic concentrations in top predators. Oil spills, whether from tanker accidents, offshore drilling disasters, or routine releases from ships, contaminate coastal waters and harm marine life. Perhaps most pervasive is plastic pollution. Plastic does not biodegrade in any reasonable time frame. Instead, it breaks into smaller and smaller pieces, creating microplastics that are now found throughout the ocean, from surface waters to the deepest trenches, from polar ice to tropical beaches. Marine animals ingest plastic, mistaking it for food, leading to starvation and poisoning. Plastic debris entangles marine mammals, sea turtles, and seabirds. Every year, millions of tons of plastic enter the ocean, and while efforts to reduce plastic use and improve waste management are increasing, the problem continues to grow. Climate change represents perhaps the most significant long-term impact on the ocean. Beyond warming and acidification already discussed, climate change is altering the fundamental structure of marine ecosystems. Species are shifting their ranges poleward as waters warm. Coral bleaching events are becoming more frequent and severe. The timing of biological events like spawning or migration is changing, sometimes disrupting the synchronization between predators and prey or between organisms and their food sources. Yet, there is also growing recognition of the need to protect and restore ocean ecosystems. Marine protected areas are being established in many regions, setting aside portions of the ocean where human activities are restricted. These areas can serve as refuges for threatened species, sources of larvae to replenish fished populations, and natural laboratories for studying ecosystem function. International agreements aim to reduce pollution, regulate fishing, and protect vulnerable habitats, though enforcement and compliance remain challenges. Scientific research continues to expand our understanding of the ocean, from the smallest microbes to the largest whales, from ancient geological processes to current changes in chemistry and circulation. This knowledge is essential for informed management and conservation. We cannot protect what we do not understand, and much about the ocean remains to be understood. Individuals can also make choices that reduce their impact on the ocean. Consuming sustainably caught seafood, reducing plastic use, supporting policies that protect the ocean, and educating others about ocean issues all contribute to conservation efforts. The ocean is vast, but it is not infinite. It can be damaged, and in some cases that damage may be irreversible. Yet the ocean also has tremendous resilience if given the opportunity to recover. The relationship between humans and the ocean is at a crossroads. For centuries, we treated the ocean as an unlimited resource and a bottomless dumping ground. We are now recognizing that this approach is unsustainable. The ocean that has supported human civilization, that has regulated climate, produced oxygen, provided food, and inspired wonder, is changing because of our actions. Whether those changes lead to degraded ecosystems and impoverished human societies, or whether we choose a different path that allows both humans and marine life to thrive, depends on decisions being made now and in the coming decades. The ocean's mysteries and future. Despite centuries of exploration and decades of intensive scientific study, the ocean retains profound mysteries. These are not the romantic mysteries of sea monsters and lost cities, though those stories reflect our long fascination with the unknown depths, but rather scientific mysteries that challenge our understanding and promise new discoveries. One fundamental mystery is the full extent of marine biodiversity. How many species live in the ocean? Estimates range from hundreds of thousands to potentially several million, but most have never been formally described or studied. Every deep-sea expedition discovers new species. Even in coastal waters, careful examination reveals cryptic species. Organisms that look similar but are genetically distinct and reproductively isolated. The ocean may harbor more biodiversity than terrestrial ecosystems, though much of it remains undocumented. Migration patterns of many marine species remain poorly understood. Sea turtles navigate across entire ocean basins to return to specific beaches to nest. Salmon home to the exact stream where they were born after years in the ocean. Great white sharks and orcas make long-distance migrations that researchers are only beginning to map using satellite tags. How these animals navigate, what cues they use, and why they follow specific routes are questions still being answered. The deep ocean holds perhaps the most mysteries. Less than 20% of the seafloor has been mapped in detail resolution comparable to what we have for Mars or the Moon. Vast areas remain unexamined. What ecosystems exist in unmapped trenches and canyons? What species inhabit regions no one has visited? What geological features and processes remain undiscovered? Hydrothermal vents were discovered less than 50 years ago, revolutionizing our understanding of where life can exist. What other ecosystems might be discovered? Cold seeps, where methane and other hydrocarbons leak from the seafloor, support chemosynthetic communities similar to those at hydrothermal vents. Methane clathrates, ice-like substances containing trapped methane, are found in seafloor sediments around the world, representing an enormous reservoir of carbon whose stability is affected by temperature and pressure. Could other energy sources support different types of ecosystems? The role of marine microbes in global processes is another area of active research. Microbes mediate nearly all chemical cycles in the ocean, from nitrogen fixation to decomposition to sulfur cycling. They form the base of many food webs and influence ocean chemistry on a global scale. Yet most marine microbes cannot be cultured in laboratories, making them difficult to study. Modern genetic techniques are revealing astonishing microbial diversity and metabolic capabilities, but much remains unknown about what these organisms do and how they interact. Looking forward, the ocean's future depends largely on how climate change unfolds and how human societies respond. Under current emission scenarios, ocean temperatures will continue to rise, potentially by several degrees Celsius by the end of this century. Sea level will rise further, displacing millions of people in coastal areas. Ocean acidification will worsen, affecting marine life in ways we are only beginning to understand. Oxygen minimum zones will expand. Changes in circulation patterns could alter the distribution of nutrients and thus biological productivity. These changes will not be uniform. Some regions may become more productive as nutrients are redistributed, though others will become less so. Species adapted to narrow temperature ranges may face extinction if they cannot shift their ranges. Coral reefs may transition to ecosystems dominated by algae and organisms more tolerant of warm, acidic conditions. Fisheries will be affected, potentially declining in some regions while shifting to different species or locations. However, the ocean also offers potential solutions to some challenges. Marine renewable energy, including offshore wind farms, wave energy, and tidal power, could contribute to reducing greenhouse gas emissions. The ocean's capacity to absorb carbon dioxide, while limited and not without consequences, has slowed atmospheric carbon accumulation. Research into enhancing this natural carbon sequestration through methods like ocean alkalinity enhancement or artificial upwelling is ongoing, though these approaches raise questions about unintended consequences and ecological impacts. Marine protected areas, if well designed and enforced, can help ecosystems adapt to change by maintaining biodiversity and ecosystem function, which increases resilience. Restoration of coastal ecosystems like mangroves, seagrass beds, and salt marshes not only benefits marine life, but also protects coastlines from storms and erosion, stores carbon, and provides habitat for commercially important species. Advances in technology will enable better ocean exploration and monitoring. Autonomous underwater vehicles can survey the deep sea without risking human life. Satellite observations provide global coverage of surface conditions. Sensor networks can monitor ocean conditions in real time, providing data for weather forecasting, climate monitoring, and understanding ecosystem changes. Genetic techniques allow researchers to study organisms and ecosystems in unprecedented detail. International cooperation is essential for protecting the ocean. The ocean recognizes no national boundaries, and many threats, from overfishing to pollution to climate change, are global in nature. International agreements and organizations work to coordinate conservation efforts, manage shared resources, and address common challenges. These efforts have had successes, such as the recovery of some whale populations following bans on commercial whaling, and the adoption of regulations to reduce pollution from ships. The decisions made in the coming decades will determine the ocean's trajectory. Will we continue current patterns of exploitation and pollution, accepting degraded ocean ecosystems as the price of economic growth? Or will we choose a path that balances human needs with ocean health? Recognizing that a healthy ocean is essential for human well-being. The choice is not between humans and nature, but rather recognizing that human prosperity depends on the natural systems that support us, including the ocean that covers most of our planet. Perhaps most importantly, we need to maintain a sense of wonder and curiosity about the ocean. It is easy to think of the ocean as a resource to be used or a problem to be managed. But it is also a realm of extraordinary beauty, complexity, and mystery. It is home to creatures that rival any fantasy in their strangeness. It contains places as remote and alien as another planet. It holds secrets about Earth's past and clues to its future. The ocean shaped our evolution, influences our climate, provides oxygen we breathe and food we eat, and continues to surprise and inspire us. As you drift toward sleep tonight, imagine the ocean continuing its eternal rhythms. Waves breaking on shores around the world. Currents flowing like planetary arteries. Phytoplankton drifting in the sunlight, producing oxygen. Bioluminescent creatures glowing in the darkness miles beneath the surface. Whales singing songs that travel hundreds of kilometers through the water. Coral polyps building reefs grain by grain. The ocean breathing, living, changing, always in motion, yet following patterns established over billions of years. Closing reflection. We've journeyed together tonight from the ocean's violent birth in volcanic plumes and asteroid impacts, through the architecture of mid-ocean ridges and trenches, across the surface currents that distribute heat and life, down into the bioluminescent depths where life exists in forms barely imaginable, and forward to consider the ocean's uncertain future in a changing world. The ocean is more than just a body of water. It is a fundamental part of Earth's system, inseparable from atmosphere, land, and life. It is ancient, yet constantly renewing itself through the water cycle. It is vast, yet vulnerable to human impacts. It is mostly unknown, yet familiar to anyone who has felt its waves or tasted its salt. You carry the ocean within you. The water in your body has passed through the ocean many times. The salt in your blood echoes the composition of seawater. The oxygen you breathe was produced in part by marine phytoplankton. The climate that makes your region habitable is moderated by ocean currents. The evolution of your ancestors was shaped by the ocean they crawled out of hundreds of millions of years ago. You are not separate from the ocean. You are part of it, a temporary pattern in the great cycle of matter and energy that flows through the biosphere. Tonight, as you rest, the ocean continues its work. Tides rise and fall under the moon's pull. Deep currents carry cold water from polar regions toward the tropics. Phytoplankton divide, doubling their populations. Fish migrate. Whales sing. Sharks hunt. Coral polyps extend their tentacles to feed. In the deepest trenches, creatures you cannot imagine go about their lives in the dark. The ocean doesn't sleep. It flows, circulates, lives, breathes, and endlessly renews itself. The story of the ocean is the story of Earth itself. From a molten beginning, through billions of years of evolution and change, to the blue planet we inhabit today, the ocean has been central to every chapter. It will continue long after humans are gone, though what form it takes depends in part on what we choose to do now. We have the knowledge to protect it, the technology to monitor and study it, and the capacity to make choices that allow both human society and ocean ecosystems to thrive. Whether we will make those choices remains to be seen. If you're still awake and have found some peace or wonder in tonight's exploration, I'd be grateful if you'd consider subscribing to the channel and leaving a like. It helps others find these calm journeys through science and nature, one sleepy explorer at a time. There are more topics waiting to be explored, more mysteries to ponder as you drift off to sleep. For now, let the thought of the ocean comfort you. Its vastness puts our concerns in perspective. Its rhythms remind us that change and constancy coexist. Its depths hold mysteries that inspire curiosity. Its role in the planetary system reminds us that everything is connected. Sleep well, rest deeply, and know that as you sleep, the ocean continues its ancient dance, covering most of the planet in its embrace, following patterns established billions of years ago, yet always changing, always adapting, always alive. From the surface lit by sunlight to the depths that know only bioluminescent glow, from tropical reefs to polar ice, from coastal waves to abyssal plains, the ocean surrounds you, connects you to all life, and gently carries you toward tomorrow. Good night.